Good day, I'm Norman Wildberger. As you probably suspect, I'm not a big fan of 20th century mathematical work in the foundational level. I think that we are collectively living in a dream world with objects and constructions that aren't pegged down to reality. And one of the jobs of this foundational series is to try to move us gently, or perhaps not so gently, in a more realistic and more honest direction. Now, one of the aspects of this that I'm going to talk about today is the movement from a 20th century object-oriented point of view to a 21st century expression-oriented point of view. I want to tell you what those terms mean to me and give you some applications of these thinkings to algebraic curves. We're ultimately wanting to understand algebraic curves in a good way, and this is a very pertinent discussion. Even though it's sort of at the meta-mathematical level, I won't actually be giving mathematically precise definitions of these terms object-oriented and expression-oriented. But I hope you'll get the gist of it and it will resonate with you. Okay, so very roughly, one of the aspects of 20th century mathematics is that it has been object-oriented. So people have had this idea that there are mathematical objects that are out there. They're often almost physical in the sense that we can picture them, maybe we can graph them or we can model them. And the idea is that we should try to model those inside mathematics. So we take the abstract picture and we try to build up some structures that reflect as accurately as possible these images that we have. I believe that 21st century mathematics is going to take a quite different approach to things, where the primary things of interest are not necessarily mathematical objects, but rather mathematical expressions. So, 20th century mathematics, of course, has many things good about it, and many things also not so good about it. Some of the things that are not so good about it is that it's based on Cantor's set theory and sort of a notion of functions that goes along with set theory. This is unfortunately an infinite set theory, and it has all kinds of waffly aspects, all kinds of imprecisions associated to it. There's all kinds of wrong habits of thinking associated with this. Unfortunately, it's become very much an orthodoxy, and I'm going to have an uphill battle trying to convince you to think clearly about this subject from the beginning again. Nevertheless, I will try to do that. Another aspect of 20th century mathematics, it has a very descriptive approach to definitions. Definitions in the 20th century are sometimes not much away from being descriptions. There is not really a distinction between a description and a specification. In the 21st century, I believe that specifications and definitions will be much closer together. People will not be looking for sort of a painting of a definition, but actually asking the question, how do we specify mathematical objects? 20th century mathematics has the idea that we try to lock in interpretations. We have some mathematical object, we want to lock in an interpretation of that mathematical object. I believe 21st century mathematics is going to be more flexible and going to allow and in fact encourage multiple interpretations of the expressions that are involved. You'll see what I mean. I'm going to amplify this to some extent, but I just want to lay this out for now, so give you something to think about. 20th century mathematics has also been very oriented towards human visual and tactile processing. The models and the arguments that are used are often very close to visual reasoning. I believe that in the 21st century we're going to have to move to a more computer-oriented frame of mind, where it's less human-centered and more computer-centered. In fact, sort of when in doubt about a mathematical construct or mathematical definition or mathematical argument, when there's debate about whether something makes sense or not, I think a good way of going forward on that is to ask ourselves, can we encode this on a computer? Is your definition precise enough, clear enough, that somebody can encode it on a computer? Is your computation explicit enough that it can be encoded on a computer? It's some kind of litmus test that gives us more certainty than a lot of talk. Okay? There's a lot of talk in 20th century mathematics, which is largely unsupported by computer equivalence. All right, so I want to explain some of this business. It's going to take me more than one video to do that. There's many aspects of this, but it's a general orientation that I've had throughout this series. You've probably noticed it in several spots, and now it's time to be a little bit more specific about what the differences are and how it manifests itself. Today we're going to look at this distinction in rather only one special direction. The direction that we've been talking about in the last few videos having to do with algebraic curves. That's sort of the application that we have in mind. But in fact, I'll have a lot more to say about this in subsequent videos, in other aspects of mathematics. But for today, we're going to look at how does this actually sort of practically look like in our study of curves. And to make things very simple, we're going to keep things down to the simplest curves. So let's have a good look at a very simple example. The unit circle. What is the unit circle? In the 20th century, of course, we have this pictorial representation of it, what we draw in the XY Cartesian plane. But the actual definition of it in most textbooks will be pretty well this one here. To the 20th century mathematician, a circle is a set. It's a set of points. So it's the set of points x, y, where x and y are real numbers that satisfy x squared plus y squared equals 1. All right, there's all kinds of problems with real numbers that eventually we're going to talk at length about. But let's accept that for now. So what does this mean? Well, it's a set. So it's got a lot of elements. And each element in the set looks like this. It's a point, so it's got some brackets. And inside the brackets are two numbers. And those are real numbers. And they have to have this property. All right, so inside this set, for example, we would find the point 1, 0. Because 1 and 0 satisfy this equation. We'd also find 0, 1. We'd find 3/5, 4/5. We'd find 1 over root 2, 1 over root 2. We'd find 5/13 minus 12/13. 0 minus 1. But of course, this is sort of unrepresentative. Most of the numbers here are wildly much more complicated than these ones. So for example, you can let x be pretty well anything, as long as it's in the range between -1 and 1, say e to the minus 2, and then y will have to be something like square root of 1 minus e to the minus 4. So you can write down something like that, and then you think of this set as sort of carrying on and on and on. That's what a circle is. So if you want to write down what the circle is, you really are obliged to write down this set. Of course, we can never write down this set because of the complexity involved in these three little dots, which are just tucked away back here, almost beyond notice. But it's these three little dots, of course, that contain all the complexity. That vast collection of bigger and bigger ordered pairs with wilder and wilder numbers in them. In fact, this is not really an honest representation at all, because it suggests that you can actually list the pairs in some kind of order. Well, according to the standard dogma, this infinite set that we're talking about is not really at all of this kind. It's not actually countable, according to the standard dogma, okay? So what that means is that the level of infinity that's supposedly being involved here is larger than the infinity of natural numbers. Okay, and there's so even this representation is somehow completely inadequate. This kind of idea is very much a 20th century idea. In previous centuries, older civilizations, they would never have thought about it this way. I'm not sure how they would have explained what a circle is, but certainly not in this way. This is vastly too complicated, and there's somehow dishonesty oozing out of all corners of this definition. But repetition renders the ridiculous reasonable. If you repeat something, even if it doesn't make a lot of sense, but you repeat it enough times, eventually it starts sounding more and more reasonable. The young student today, mathematics student, is exposed to this kind of set repeatedly, over and over. Everything is defined in terms of some kind of set. So you become oblivious eventually to the logical obscurity of the concept. A circle to us, to an artist, is something that's continuous. It's something that you draw like this. It's not something that you create by drawing a lot of points. Okay? This is like a pointillist kind of definition, where you making a lot of points like this, like the Impressionist school of painting, which was quite popular for a little while. This is really a pointillist definition, and somehow does not reflect the physical aspect of what we're doing when we're drawing a circle. There's something very fishy and very unpleasant, really, about such a definition, in my opinion. It's way too complicated. So I believe that in the 21st century, we're going to move back to a simpler and more naive approach to things like the unit circle. Earlier generations would have said, well, a unit circle, the essential part of it is this equation here. It's this equation here that really captures the circle. And some mathematicians would have said that the circle is that equation. And I think that's a definition that needs to be taken seriously. That the circle really is encaptured by this equation, and that equation is really reflecting the circle. This is a lot simpler than some vast infinite set with all kinds of complicated ordered pairs in it. However, we want to go a little bit further, because this thing here already has some ambiguity in it because of the x and the y, which are variables, not something that we've really pinned down. But we know that we can replace something like this with an associated Pauli number. Actually, a bi-Pauli number, but I won't always say that. So instead of x, we might use alpha. Instead of y, we might use beta. And then we're really talking about this bi-Pauli number. A minus 1, no betas, 1 beta squared, no alphas, 1 alpha squared. So this little bi-Pauli number really kind of encodes the circle. However, there's a bit of ambiguity left, because we can in fact scale this equation and still have the same circle. In other words, if you come along and you multiply both sides of this equation by 2, for example, you get 2x squared plus 2y squared equals 2. That also defines exactly the same circle. And this equation corresponds to the Pauli number 2p equals minus 2, 0, 2, 0, 2, if we bring everything to one side. So if we're going to associate the circle with a Pauli number, should we associate it to this one, or should we associate it to this one, or some other multiple? Because the actual Pauli number that we use, if we scale it, we get the same geometrical object. So we have to incorporate that somehow into the definition. So we're going to make a small modification to the idea of a Pauli number or a bi-Pauli number. We're going to talk about a projective bi-Pauli number. So here's a projective bi-Pauli number. It looks a lot like a bi-Pauli number, except that instead of having sort of one half bracket around it, it has a double half bracket around it. That's going to be our convention that tells us that this thing is unchanged if we multiply by a non-zero number. So we're going to agree that this double bracket tells us that we are allowed to multiply the thing by any non-zero number and it doesn't change. So this projective bipolar number is the same as this projective bipolar number, which is the same as this one. And we might just use a capital P instead of a small p for the projective object. Okay, so now we can say, what is a unit circle? Here's a 21st century definition, which is not really that much different from probably a 17th century definition or an 18th century definition, except it's a little bit more formalized, a little bit more computer amenable. The unit circle is the projective bipolar number C, this one right here, minus 1, 0, 1, 0, 1, with the double brackets telling us it's a bipolar number. That's projective. That's an expression. When you look at it, you cannot see a circle immediately. You have to interpret it in a way so that you get a circle. But the expression actually has a variety of interpretations. And this is where things get interesting. The expression is this, but the interpretations can be many. Let's have a look at a couple of different interpretations of this expression. So our first interpretation, which we'll call interpretation A, is the standard one, the one that we really started with. So here is our projective bipolar number, C, and here it is written out as a bipolar number in sort of alpha-beta form, minus 1 plus alpha squared plus beta squared. And I put a little bracket around here, sort of telling us that this is a projective quantity. It's not exactly a bipolar number, because if we multiply it by 5, it's unchanged. That's what the meaning of those brackets is. Okay, so how do we interpret this object? Well, we associate to it this equation. The equation obtained by replacing alpha with x, beta with y, and setting the bipolar number equal to 0. So I've set it equal to 0, and then I happen to have brought the 1 on the other side to make it more familiar. But it's really the setting this equal to 0 that's the crucial thing. And note that if we multiply this by 5 and set it equal to 0, it's the same as if we just set this thing equal to 0. That extra factor or scaling factor that's in there doesn't have any effect when we set it equal to 0. So it's a well-defined thing to do. So we start from the projective bipolar number, we get an equation, x squared plus y squared equals 1. And then we can visualize that, well, actually, in a number of different ways. We can look for those points, x and y, that satisfy this equation, and plot those points in the standard Cartesian form, and we get the circle that's familiar to us. But somebody else can come along and say, well, actually, I prefer a projective point of view. I prefer to imagine the Cartesian plane as a horizontal plane, and I'm looking at it from some vantage point with the horizon here. So there's the y-axis, there's the origin, there's the x-axis, and then the various lines, y equals 1, y equals 2, y equals 3, will be spread out ahead of me, increasingly closer and closer together as they march towards the horizon. And the various lines, x equals 1, x equals 2, x equals 3, they will be like railroad tracks, all meeting at this point at infinity because they're parallel over here. Now if I draw the unit circle in the same sense, I look at all the points here that I can that satisfy the equation, plot a lot of them and join some up with some lines, then what will appear is something that's not quite a circle. It'll be more elliptic. In fact, it'll be exactly an ellipse. But nevertheless, that's a picture, almost like a photograph of this thing if it were lying in a plane and you actually took a picture of it with the horizon there as well. Here's another variant where we still have Cartesian axes, but the spacing in the x and the y directions are different. Why not? That's sometimes useful. And then when we plot the points that satisfy this, we get a shape which is again an ellipse. It's a stretched circle which is an ellipse. Another variant on that is this one over here, where we've taken our axes to be not rectangular. x-axis in this direction, y-axis up there. Perhaps not equal scaling. We can still plot the points x and y that satisfy the equation. When we do so, we'll get another ellipse. This is an affine transformation of this one. And now let's enlarge our thinking even more. Let's suppose that we're visited by a creature from outer space, which is blind and doesn't have nice hands like we do. It has some very broad sort of planks that it uses for hands. So anything that's two-dimensional is pretty well invisible to it. It needs to feel something three-dimensional in order to get a sense of what we're talking about. So to such a creature, if we wanted to represent our unit circle, drawing it on a piece of paper or even raising it a little bit like in a braille would not be good enough. But what we could do is we could build a cylinder on top of this thing. So here's a picture of the XY plane now sort of horizontally laid out. This unit circle here is now along here. And I've built a cylinder on top of it. So our friend from this other planet could come along and could feel this cylinder and say, ah, that looks like the unit circle. Ah, you know what you're talking about. You're talking about the unit circle. He can feel that. In fact, anything that you can represent two-dimensionally, in terms of some kind of curve or conic or whatever you have, you can always sort of extend it up, directly up, making a three-dimensional model, essentially, that this entity could get a grasp of by grasping this, so the sides of it rather than just the base. So maybe from that person's point of view, or that creature's point of view, this thing really ought to be interpreted as this cylinder type of object. It really contains the same amount of information if we agree to always go vertically up. The unit circle, the cylinder built on top of it, pretty well equivalent. Here's a variant on that where we, for some reason, agree to take our unit circle in the base plane XY and to build a three-dimensional object which obtained by drawing all kinds of lines from the circle up to a particular point above it. So kind of some kind of cone. So we can imagine some other kind of creature which is physically oriented so that it can feel that kind of object, maybe not this kind. To such a creature, they could feel this and say, ah, that looks like a unit circle. So again, there's something equivalent about whether we're talking about the circle or whether we're talking about this cone built on top of it. They're all possible visualizations of this. So this is the idea that to say that a circle is exactly this is a little bit too limiting. It's too narrow-minded. There are different ways of thinking about a circle. That equation is actually more fundamental than any of these pictures. And more fundamental than that equation is this projective bipoly number from which the equation comes. That's the expression. These are various pictures, visualizations, interpretations of the object. So that was interpretation A. Now I'm going to give you a quite different interpretation. Same unit circle, represented as a projective bipoly number. There it is again. But now we're going to look at that and associate to it something rather different. We're going to associate to it the graph z equals minus 1 plus x squared plus y squared. So we replace the alpha with the x and the beta with the y as before. And now we have a third variable, or a third polynumber if you like. And we're going to plot points with three coordinates. Coordinate x, coordinate y, and the z, or the third coordinate, this value here, minus 1 plus x squared plus y squared. We're going to plot that for various points x and y in the base plane, and then somehow or another we're going to join the dots to get some kind of surface. Okay, so what does it look like? Well, here is a representation of three-dimensional space. It's a pretty well standard representation. I don't think I've talked very much about this. There's an x-axis here, a y-axis here, and a z-axis going up. When looking at it, you should think of this x-axis as coming out at you, and the x and y-axes as sort of being on a horizontal plane, with the z-axis being vertical. Now, for a little bit more information about this three-dimensional setup, I recommend my Wildlin Alg number 9 lecture, which is three-dimensional affine geometry, which gives us more detail about what this coordinate system looks like. So what we're planning to do here is we're going to take various points in the xy plane, for example, say the point 2, 1. So the point 2, 1 is there, and in the plane it would be the point roughly like there. And then we evaluate this thing here at the point 2, 1. So let x be 2 and y be 1. We get altogether 4, telling us that the z coordinate associated to this point would be 4. So we're going to plot 2, 1, 4, which is some point which is on this surface, and the surface is in green. It's an elliptic paraboloid. It's actually a circular paraboloid. It means it's like a parabola, except that it's been rotated. Okay? And a cross-section is, in general, an ellipse. This is a very circular one, so if you take the cross-section, you actually get the unit circle. So in other words, if z equals 0, and we're just looking at the cross-section of this thing, so slicing it where it meets the plane z equals 0, in other words, the xy plane, then we're getting the unit circle that we were talking about before. Now, you may notice that in my scaling of this three-dimensional reference frame, I have the x coordinates scaled and the y coordinates scaled, and along the z coordinates I have some markings, but I don't have any numbers. Why didn't I have any numbers? Well, because we're actually thinking of this bipoly number only up to scaling. If we multiply it by 5, it's really the same projective object. That means if we multiply this by 5 and replace this with 5 times itself, we should really end up having the same object. That will not happen if I actually introduce scaling, like 1, 2, minus 1. Then I will have a specific elliptic paraboloid. By avoiding to scaling here, I'm incorporating this scaling that's the projective aspect of this bipoly number. So in other words, with one type of scaling, this might be 1 and this might be 2. With another scaling, this might be 2 and this would be 4. With another scaling, this might be 100 and this might be 200. So this picture represents all of them somehow at once. It's a bit of a trick to incorporate the projective aspect into a diagram. It's really well worth thinking about this, okay? So what we've done is, instead of thinking about the unit circle as this circle in the usual way in the xy plane, we're now thinking about some larger object, a surface in three-dimensional space, whose cross-section happens to be that original circle. Now both of them came from this bipoly number. So it's really only a point of view that separates the two. You can say, this is the circle. Someone else can say, no, no, this is the circle. You're both just interpreting the expression. Neither of you can claim to be completely correct. Both of you are just expressing a point of view about how to interpret the expression. Which is a better way might depend on the application. It might depend on the richness of results and understanding that result. We're going to see that this, in fact, this interpretation B, is a very powerful way to think about what a unit circle is. It's a very powerful way. So please give this some serious thought. It might be a little bit novel thinking to you, to think of this unit circle as actually being that elliptic paraboloid. So to better understand the distinction between these two interpretations, let's go back to a simpler one-dimensional situation. We're going to consider the case of just a polynumber instead of a bipolynumber. But it'll be a projective bipolynumber. So suppose that we consider this projective polynumber, minus 6, 1, 1. And it's written in kind of row form, so probably we should use betas. So there it is there, it's minus 6 plus beta squared, and it has little brackets in here telling us that it's a projective object, meaning if we multiply it by 7, it really hasn't changed. Okay, so there are two possible interpretations to what this thing is. One is interpretation A, which, analogous to the previous discussion, would say the following. What we need to do is we need to take this thing here, replace betas, say, with x's to make it a little bit more familiar. So now we have minus 6 plus x squared, and we set it equal to 0. And we look for solutions. So we're setting the thing equal to 0 and looking for solutions. There's only one variable, so there's only one line on which the solutions can live. We're talking about x values that satisfy this quadratic equation. And I hope you can all solve that quadratic for us. So x equals 2 is one solution. And we get 4 plus 2 minus 6, that's 0. And another one is minus 3. That would be 9 minus 3 minus 6, it's also 0. So that's a picture of the solutions to this equation. This is sort of a one-dimensional analog of the picture of the unit circle, which was x squared plus y squared equals 1. Solutions to that, solutions to this. Now the second interpretation, interpretation B, what is it going to do? It's going to associate to this same polynumber a graph. We're going to introduce another variable, say y, and we're going to graph y equals minus 6 plus x squared, going from one dimension to 2 dimensions. So that's the kind of thing that we've been talking about graphing polynumber. And okay, it's a parabola. It looks like this. I've deliberately left the scaling on the y-axis out so that, well, so that the scaling which is inherent here is reflected in this picture. And notice that the parabola that we get has to go through the points 2 and minus 3. So the cross-section of the parabola by this line gives us the one-dimensional picture of interpretation A. This interpretation B is a bigger picture that somehow is telling us more, but it maybe is more work to get it. But maybe not, because in fact we don't have to solve any quadratic equations to graph it. We just have to plot a lot of points, which is straightforward but laborious perhaps if we want a good picture. So please make sure you understand how this distinction in this smaller case is an exact reflection of the distinction between interpretation A and interpretation B of the unit circle that we talked about. Okay. Well worth really giving these things some careful thought. So let's go back to our unit circle. We had these two interpretations, interpretation A, interpretation B. I want to now talk about another example, another important example. In fact, I want to talk about the second most important circle. The unit circle is the most important circle. This one is the second most important circle. Let's have a look at it. Its name is D. It's also given by a projective polynumber. It looks a lot like the unit circle one, except that instead of having a minus 1 here, it has a plus 1. As a bipolynomial in alpha and beta, it's 1 plus alpha squared plus beta squared, projectively. Now let's look at this thing from those two different points of view, interpretation A, interpretation B. So, interpretation A. What we do is we associate to this thing an equation obtained by replacing alpha with x, beta with y, setting everything equal to 0. So if we set everything to 0, and then maybe we can bring the minus 1 to the other side. We get x squared plus y squared equals minus 1. And now what we should do is we should graph as many points that satisfy this as we can find. Okay, but x squared plus y squared equals minus 1, that's not really a circle in the standard framework, because there are no points x and y that satisfy that equation. X squared and y squared are always positive. When you add them, you still get a positive number. You're not going to get minus 1. Not until we go into the complex numbers, which we have not talked about yet. So over the rational numbers, no solutions. The picture of this thing is empty. It seems like there's no solutions. This is completely uninteresting. How can Weilberger possibly say this is the second most important circle? It doesn't even exist. Well, depends on how you look at it. Let's look at it with the eyes of interpretation B. What do we do there? We associate to this thing a graph. We take the same expression, 1 plus x squared plus y squared, introduce a third variable, say z, and then we're going to graph z equals 1 plus x squared plus y squared. Okay, there's our axes again, x, y, z. You might want to play around with this if you haven't much experience with this kind of three-dimensional plotting, trying to visualize what happens. That's made easier sometimes by setting one of the variables equal to 0, for example. You might set y equal to 0 and see what happens. That's sort of this cross-section. That'll be a parabola. Or set x equal to 0. Or set z equal to 0. If you set z equal to 0, well, then we're back to this equation here. We're asking, where does this thing intersect the xy plane? The answer is nowhere. And we can see geometrically why it doesn't have solutions, because this graph is one of these elliptic paraboloids, same kind as we saw earlier, except that it's based up here rather than below. So it's just going up from here. There's no way it actually meets the xy plane. But nevertheless, it's just as pleasant a geometrical object as the elliptic paraboloid that we got for the unit circle. So with this interpretation B, suddenly we're getting something. We're seeing something that we don't see with interpretation A. All right, that's good. But there is more. There is a third important interpretation. Interpretation C. Ultimately, perhaps interpretation C will be even more important than interpretations A and B. We're going to see later on in this series, when we start talking about algebraic geometry more, how the idea contained in this slide ends up having very big ramifications. Okay, so this is a tip of an iceberg, and I'm just touching on it now to plant some seeds into your minds. What is interpretation C? Well, here is our unit circle again. It's minus 1 plus alpha squared plus beta squared. We're going to take this thing and we're going to associate to it something slightly new. We're going to associate to it a correspondence between 2 points in the plane. So instead of having just a single point xy and asking, does x squared plus y squared equals 1, we're going to take 2 points and ask something about both of those points. So the point A1 is x1, y1, the point A2 is x2, y2, and we're going to ask, is x1 times x2, which is replacing the alpha squared, plus y1, y2, which is replacing the beta squared, equals to 1. So in the interpretation A, we had x squared plus y squared. Now we're breaking that x squared into not x times x, but x1 times x2. And we're breaking the y squared into y1 times y2. This makes things a little bit more complicated, but it also makes things dramatically simpler. How? Well, first of all, it makes things more complicated because there's 2 points now instead of 1. We're talking about a relationship between 2 points. So what we're saying is that if there's a point A1 and there's a point A2, then these 2 points may or may not satisfy this correspondence. Okay? Most of the time they will not satisfy this, but every so often they will satisfy this relation, and then those 2 points are special. So we want to graph kind of both of them at once. We want to find all pairs that satisfy this relation. That sounds more complicated, but what makes it simpler is this observation. That if you fix one of the points, you fix it and you ask the question, what are the points A2 which are in correspondence with that fixed A1? Then it's a linear equation in the coordinates of x2. You're getting a line. So the points A2 which are in correspondence with a fixed A1 lie on a line, and conversely. So I'm going to leave it to you as an exercise to sketch a number of these lines. So for example, if we're talking about the point 2, 0, if A1 was 2, 0, then this equation would read, that's a 2 and that's a 0, so that term would die. It would be 2x2 equals 1, or x2 equals 1/2. That's an equation. x2 equals 1/2 represents this line right here. So all the points which are in correspondence with 2, 0 are the points lying on this line. This is called the polar pole correspondence, and it plays a very big role in projective geometry. It's a very important way of thinking about the unit circle. And in some sense, it's the most important aspect of a unit circle. And just to give you a little bit more examples, the polar of this point here is this green line here. The polar of this point here is this blue line here. The polar of this black point is this black one here. And you can see perhaps that if the blue point lies on the red polar, then the red point lies on the blue polar. You can maybe investigate why that is. This is just a very brief introduction to this idea. We're going to talk more about this later. I want to get you to think about the idea that there are more than one interpretation. Let's have a look at this interpretation of the second most important circle, that invisible circle that we introduced. Okay, so let's have a look at this circle D. 1, 0, 1, 0, 1, 1 plus alpha squared plus beta squared. So we're going to associate to that the correspondence between these 2 points given by this equation. Same as the last one, except there's a -1 now on this side instead of a +1. Okay, so here now I've explicitly shown you the lines that you get that correspond to various points A1. If A1 is 2, 1, then we get the line 2x2 plus y2 equals -1. And if A1 is -1, 1, then we get the line minus x2 plus y2 equals -1. And if A1 is the line 0, -1, we get the line that's 0 minus y2 equals -1, or y2 equals 1. So this is the first case. If A1 is up here at the point 2, 1, then here is its polar line. If A1 is the point -1, 1, which happens to lie on this polar line, then its polar line of this point is this line here. And if A1 is 0, -1, the point where they happen to meet, then the polar line, I haven't drawn it, is the line y2 equals 1 would go through those 2 points there. It turns out that this pole-polar relationship is very, very important. Okay, it's crucially important for many things in geometry, but and I'll explain that at some later point. So the message today is I've just started to introduce this idea that expressions are more important than objects. Okay, this maybe goes against our highly visual nature. We like to see things, and that's good. Okay, but our computers prefer expressions, concrete, explicit expressions with numbers, preferably. Numbers arranged in nice, concrete, organized fashions. So this point of view expressions are primary, objects are something that are secondary, that are associated to expressions, and there may be various ways of associating objects to expressions. There may be different interpretations. I think this is a very powerful and somewhat novel idea. Okay, somewhat novel idea. Next time we're going to develop the implications of having this interpretation A and interpretation B of something like unit circle. So in fact, we're going to talk about calculus on the unit circle and on this imaginary circle, the second most important circle. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.